In this video, we'll be covering a few more temperature sensors, specifically thermocouples and RTDs. So firstly, thermocouples. Well, thermocouples basically use what's called the Seebeck effect, or sometimes called the thermoelectric effect. Now, what is this? Well, in 1822, Thomas Seebeck observed that if you had two dissimilar metals, so two metals that aren't the same, you connected them together and had one of the ends of them at a hot end or heated up and one at a colder end, you could actually measure a voltage that would be induced through them. Without connecting it to power or anything like that, you would actually create a voltage itself. Now, that voltage is very small. We're talking microvolts, or if it's a high temperature that we're dealing with and we have the right metals, maybe a few millivolts, but quite small voltages. And we know that that voltage is proportional to the temperature difference between the hot end and the cold end. And so we refer to those two, hot end and the cold end, as the hot junction, the thing that we're trying to measure, and the cold junction, which is typically held at room temperature. And so this diagram that you see here, we've got the hot end and we're holding it over a candle. We have the cold end, which is at room temperature, and we actually see a voltage that's being created there as a result of that. Now, one place that you might see something like this is if you go through somewhere like JCar or you get a multimeter. Some of them will have a thermocouple attachment where you can plug a thermocouple in there and use it to accurately measure temperature. There's an example just above with that wire that's coming out is the thermocouple. So I've mentioned already about the hot junction that we use for our measurement, the cold junction that we use for as a reference point. As we heat something up, we cause more vibrations of the particles within that material. And those vibrations cause electrons to flow through to the cold end. And so we're generating a small amount of voltage as a result. Now, thermocouples have a wider range than some of our other sensors, so like minus 200 degrees to about 1200 degrees. So they're more suitable for some of our higher temperature applications. We have a number of different thermocouple types, and remembering that these thermocouples all use two different types of metal, two dissimilar metals. So there's a number of different combinations there. The most common thermocouple that we'll probably find around the place, and the one that most multimeters will have, will be the K-type thermocouple. For each of these thermocouple types, there's a calibration table that we can look up and work out the different calibration parameters and parameters to try and linearize our measurements. One thing I should mention though is, remember, these voltages that we're generating with our thermocouple are quite small, so we'll often need to amplify them up. So you see in this table, we've got some of those different thermocouple types with different temperature ranges associated with them. So some of them are only designed for degrees over 0 degrees Celsius. Some of them allow very wide ranges and very high temperatures. We also list our different sensitivities for each of these in microvolts per degree Celsius. The final column there is the ANSI designation. So is it a K-type thermocouple or a B-type thermocouple, and so on. Now, thermocouples have some pros and cons associated with them. They do have a high temperature range, significantly higher than any of the other ones that we've looked at previously, being the thermistors and the IC temperature sensors. And they're pretty inexpensive, and they typically have quite a fast response, partly because the thermal mass of those little bits of wire is actually quite small compared to some of our other devices. And they can withstand fairly rough environments where we've got significant vibration and other things like that occurring. Having said that, they do require a cold junction or that reference temperature point. They do output quite a small signal that needs to be boosted up, and it also needs to be linearized quite often as well, because they're quite non-linear in their output. They're also the least accurate of any of the different temperature sensors that we're talking about. But they're still quite accurate for many applications. And so we have some high temperature applications there, for example, furnaces and kilns, through to quite low temperature applications where we're getting quite cold, like we're trying to do cryogenic freezing. Now, these thermocouples, which use the Seebeck effect that we talked about earlier, are somewhat related to a different thermoelectric effect, which is the Peltier effect. And the Peltier effect, we essentially have an array or a whole series of these thermocouple-like dissimilar metals. And instead of, we have a Peltier picture above. And what we do with this system is if we pass a current through it, we have a separation of temperatures occurring. So one side of it becomes quite hot, hot enough to burn yourself on from personal experience, and one side becomes quite cold where any water on there actually freezes. So these are sometimes used in portable little fridges and things like that, where we pass a current through it, we can heat something up, and we might need a big heat sink or something on it to try and disperse that heat if we don't want the heat. And we can also cool something down to quite cold quite quickly. You can use these Peltiers in reverse, where if you heat one side up and cool one side down, we can actually generate electricity out of it. And sometimes you might have a furnace or something like that, or something quite hot, that you line the side of the chimney with Peltiers. And so one side gets quite hot, the other side gets quite cold or stays cooler, and we generate power that way. Our final method for measuring temperature that we'll look at, which is a contact method, is our RTD, our resistance temperature detector. Basically here, what we recognize is that the resistance of a wire, and we looked at the physics of this previously, will change with temperature. So the resistivity of a piece of wire will go up or down by a small amount we're talking about when temperature changes. And so if we have a long piece of wire, that temperature change will exacerbate that change in resistance. Typically, these RTDs use platinum, which is a super expensive metal. And it means that the price tag of these RTDs are much higher than the other sort of sensors that we've been looking at previously. Having said that, they are quite accurate. We have the resistance equation specified for these RTDs, which is a function of the resistance of the metal wire at 0 degrees or at a certain set point, the temperature that RTD is experiencing, and we have some coefficients associated with it as well, which are specific to the RTD that we're using, and we can get from the data sheet of that RTD. Now, normally when we're measuring small changes in resistance like this, we use a Wheatstone bridge. We've previously talked about Wheatstone bridges. And so we connect it up to a Wheatstone bridge. We can get very accurate determinations of temperature, but also quite expensive ones. So pros and cons, we're talking here high accuracy, the highest accuracy of any of our sensors, high resolution, and something that's quite stable for measurement. But some cons associated with that, they're very expensive, have quite a slow response time because we've got a fair bit of thermal mass that needs to heat up or cool down, and that's what we're essentially measuring. We also need to compensate for the lead resistance. Often they'll have not just 2 connections to the Wheatstone bridge, but they might have 3 or a 4th connection to the Wheatstone bridge to help cancel out the resistance of the actual wires that take this RTD sensor to our Wheatstone bridge for our measurement purposes. And they can do that self-heating as well, because they've got current flowing through here, through the Wheatstone bridge and then through the RTD, which can cause it to heat up by a small amount. Now, a lot of the applications for these RTDs are where we need really precise temperature measurement. So maybe scientific equipment or industrial equipment that requires very tight tolerances around the sort of measurements that we're taking. We also use them, for example, in chemical processing and medical research.